Y'all should have calculators. Make sure you've got calculators. Okay. We're doing some parent functions. Okay. Not today. And I'm not going to make you do them all. It's like, all right, like which, right? There's so many. Hopefully you already know many of these. If you guys that haven't taken Algebra 2, you might not know all of them. So these are all parent functions that you need to know what they look like. Parent functions are the most basic graphs that we will then shift up, down, left, right, and stretch them, shift them and stretch them to put them into new forms. And this is a very important skill, to be able to take a graph and know when we put a number in front, how does it shift it or stretch it. And so first we're starting with the parent function. So we're going to go through real fast. We are not filling all this out. So parent function, diagonal line. Do you know what this function is? Linear. This very simple is the line y equals x. Okay, very simple parent function. And it is just that diagonal line, really great. Domain and range. Remember, domain is how far left and how far right the graph goes. Range is how low and how high the graph goes. So on this graph, how far to the left does this arrow go? Infinite. Negative infinity to positive infinity. It goes forever left and forever right. How low does the graph go? Negative infinity to positive infinity. Again, that arrow goes not only to the left, but it's also going downward, all right? And same with this arrow. It's moving right, but it's moving up as well. So eventually, it's just everywhere, okay? Does it have any discontinuities? Well, what's continuous? Continuous. You can draw it without picking up your pen, right? So does it have any discontinuities? No, it does not. Okay, great. Okay, parent function. What's this one? What makes a v? Absolute value. Y equals absolute value of x. Absolute value v. That's how I remember that. And absolute value v? Always, always. Okay. Now, domain. How far left and how far right does this graph go? Infinite. Negative infinity to positive infinity. What's the range? How low does it go? 0. And how high does it go? Infinite. Very good. Do we use a bracket or parentheses? 0? Bracket. Very good. Because it's actually equal to 0 right there, we use a bracket. All right, super. Any discontinuities? No. Very good. Okay, super. See how fast we do this? All right. What graph is this one? Quadratic, x squared, very good. Y equals x squared, very good. So this is our favorite parabola, quadratic function. What's its domain? How far left and how far right? Negative infinity to positive infinity, good. What's its range? Very good. And we use a bracket at 0, again, because there's actually a point there at 0, 0. So very good. Any discontinuities? No. Even or odd? Even. It's symmetric with respect to the y-axis. It's like folding it on the y-axis. Even and odd. Very good. So I'm just, these are just little things they're all just putting together, okay? Do we know what this graph is? Cubic. That would be y equals x to the 3rd power. This is a cubic graph. Very, very cool. What's the domain? Negative to positive infinity. All right. What's the range? How low, how high? Good. Negative to positive infinity. Beautiful. Any discontinuities? Nope. It's perfectly continuous. Even or odd? Odd. Very good. Odd means it's symmetric with respect to the origin. Symmetric around the origin. Great. Doing good, right? I know, for real. There's so many, right? Yeah, they're easy. we're going to go through them today, but square root function, square root swoop. This is y equals the square root of x. I like to call this the square root swoop. I think it's important. This is a great one to know the shape of. The square root, that square root symbol, you can imagine that it looks like the actual square root swoop, right? So that's how I remember it's the square root swoop. What's the domain on this one? 0 to infinity, bracket at the 0. There is actually, the square root of 0 is 0, so it's really there. What's the range? 0 to infinity, same thing, 0 to infinity. Again, how low does it go? Right to 0 on the y-axis, and then forever up. All right, so this I like to call the square root swoop. It is not even or odd, so great. Okay. It is, so that's a good question. Is it discontinuous? It is continuous on its domain. All right, so on its domain, it's perfectly continuous, and that's what we think, okay? Even though it doesn't have a whole left-hand side here of the graph, but it is continuous on its domain. So we do call it continuous. So no discontinuity. Okay. Here, this is a cube root function. So this is y equals the cube root of x. I like to call this the breaking wave. Like when I used to teach this in Algebra 2, it's like there's the surfboard, there's me on my surfboard back when I lived in San Diego. Totally. And there's me paddling out and standing up. And do you see it? Do you see the breaking wave? Yeah, I'm like, what's the hang 10 song? I don't know. Okay. We should play it. Oh man, I wish I want a sound effects board. That would be really cool. Okay. All right. So I call this the breaking wave graph. Is this an increasing function or a decreasing function? It is increasing. Yeah, it is going uphill from left to right. So it is an increasing function. I don't know, but yeah. So I call that my breaking wave graph. It is increasing. What's its domain? Negative infinity to positive infinity. The range? Same. Negative infinity to positive infinity. Good. Any discontinuities? No. Is it even or odd? Odd. Very good. Ooh. Very good. It is odd. It is, you can imagine, they don't have the point here, but the point 8, 2 is on the curve. So the point 8, 2 is on the curve, and it is also negative 8, negative 2. So that's nice thing to know. This is the reciprocal function. Reciprocal. What does the reciprocal do? It's sort of like the opposite. So like, for instance, if I have the number 3 halves, what's its reciprocal? 2/3, yeah. So those are reciprocals. So if I have the number x, what's its reciprocal? 1 over x. There you go, ladies and gentlemen. This is the graph y equals 1 over x. It inverts every number. Okay, it is a reciprocal function, and it does not have, it's not continuous. Where is the discontinuity? Right at 0. Right here, there is a vertical asymptote at x equals 0. That is an infinite discontinuity because it's that infinite, it sort of diverges. One goes to negative infinity and one goes to positive infinity, so that's called an infinite discontinuity. It does have a horizontal asymptote as well. There's also this horizontal asymptote, and you can sort of see that. Here, y is not going to equal 0. X cannot equal 0. That comes from our denominator right here. Can I do a number divided by 0? No. No, that's a huge error. Did you ever do the thing with the iPhone when you like, hey Siri, What is 0 divided by, or sorry, what is a number divided by 0? Like, what is 6 divided by 0? Well, so once upon a time, it used to be like, that number is undefined. Imagine if you were Cookie Monster.
Oh,
And you, well, you know that. Like, imagine if you were Cookie Monster. And you had 6 cookies that you wanted to divide among 0, split between 0 friends. And then he's like, that would be very weird. And plus, you don't have any friends, so that's very sad. Like, it was just like funniest.
Very different experience with Siri.
No, my mom's iPad with Siri, I was like, what are you doing? And it would swear at me. Some reason her Siri was set up to swear back at me.
That, I wonder if there's an app for that.
My mom's tablet did that when I was younger. I'm like,
Oh, gosh. Well, I'll tell you later. They changed it so that Siri couldn't answer. Anyway, so this has a domain restriction that x cannot equal 0. And that's because the denominator. We're going to talk so much more about this, but denominator domain, the denominator, any function that we're ever given, if we have a denominator, the denominator cannot equal 0. So anytime you have a function with a denominator, we have to solve that denominator out to figure out what values we're not allowed to equal, okay? And so denominator domain, anytime you see a denominator, we need to think in our brains, oh my God, there's a domain issue here, okay? Domain means I can use every x value except this one. I'm not allowed to use 0, but every other value for x works just fine, okay? All right, what about the range? What y values are we not going to get? Yeah, y can also not equal 0. But every other y value will be just fine, okay? Every other y value is on the graph somewhere. Okay. Even or odd? Odd, very good. It is odd. And let's see, this piece here, is this piece increasing or decreasing? Decreasing, going downhill from left to right. Is this piece increasing or decreasing? Decreasing as well, decreasing. Yep, going downhill from left to right. All right. This is our exponential function. This exponential function, I like to think about this as a Superman graph. The exponential means there is an x in the exponent. X in the exponent. And so we have this function y equals, in this case, it's 2 to the x power. All right, so exponential, there's x in the exponent, x in the exponent. It's right in there. Lots of x's, okay? This is how I remember things, you guys. I'm just how to remember, all right? I call this the Superman graph because there's literally a ride in Six Flags Magic Mountain called Superman. Have you ever seen it? Anybody been? I'll have to pull up a picture of it. But it's a Superman ride, and all you do is sit on this little carriage. There's this big cart with like 40 seats in it. There's like 3 rows or 3 rows of 10 maybe, so 30 seats in it. And you sit in this big cart at the end, and they use hydraulics to like just push you out really fast. And so you go on this track, and then you go straight up. It's like zoom, okay? And that's all you do. That's the whole ride. And it's called Superman because it's like Superman flying like to the moon, right? So it's called a Superman ride. And so this is an exponential function. All right? And you just drop back down. All right. This one is 2 to the x. And I know that because if I plug in an x value of 1, what is 2 to the first power? 2. All right? So this graph is 2 to the x, but it could be a form of a to the x. So it could be 3 to the x or 4 to the x or 2.3 to the x. Okay? So this is called exponential growth. because it is growing. It is increasing. All right, so this is exponential growth because it is increasing over its domain. All right, increasing for that whole thing, exponential growth. Okay, what's the range? 0 to infinity. Now the question is it equal to 0 or parenthesis? How do you know it's a parenthesis? It does get really, 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 really close to 0, and it never hits. So let me talk about why, because there's really good logic here. If I don't have a ton of room to write this, so I'm just gonna cross out this word. I'm gonna create a little table of values here, x, y table of values for you. When x is 0, 2 to the 0, what is 2 to the any power of 0? 1, always, always, good. Negative 1. If x is negative 1, what's 2 to the negative 1? 1/2, very good. And if it's negative 2, 2 to the negative 2? 1/4. And again, if you didn't know that, you can use your calculator, right? 2 to the negative 2, you get 1/4. And if it was negative 3, it'd be 1/8. And if it was negative 4, it'd be 1/16. And if it was negative 5, it'd be 1/32. And so we just are getting smaller and smaller and smaller and smaller little fractions. All right? And we can do that forever. Forever. Okay, so it gets infinitely close to 0, and that's all that it's doing. Okay, cool. Lovely, lovely. This is a logarithmic graph. This is a logarithmic graph, and I'm going to call it y equals log. In this case, they may be base 10 of x. Log base 10 of x. I like to call this a log ride. Every time I teach graphs, I create a story. Okay, call it a log ride. Every log ride I've ever been on. You sit down in your little log, right? You sit in the little log. What's the very first thing you do in every single log ride ever? You sit in the log ride and you go up. Click, 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 right? All you do is go up, right? And you get to the top. And maybe there's a little woo, but really, you just float around and listen to, it's a small world after all, right? That's all you do. You just float around, right? It's like the boringest ride ever until maybe the very end. But we're going to ignore that. So I think about this as a log ride because all we do is we sit here and we go click, 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 up, 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 and then it just fizzles out. It grows so slowly. It's the boringest ride there ever was, okay? I love log rides, don't get me wrong, but yes, so this is how I think about a log ride and the graph to remember. This graph has a vertical asymptote here. X must be greater than 0. X must be greater than 0. I cannot take a log of a negative number. I also cannot take the log of 0, okay? And you can try it in your calculator, log of 0, error. Log of negative 2, error. It's not going to work, okay? We can only use x values greater than 0. What is the range? How low does it go? Negative infinity. And how high does it go? Infinite. It does eventually get there. It just takes freaking forever. Okay. So, the range, it gets all the y values, but we can only use x values greater than 0. Is this increasing or decreasing? Increasing. From the left to the right, we are increasing. So increasing from 0 to infinity with a parenthesis there. Okay. Is this? Yeah, okay, good. 3 more here, I can count. This is the greatest integer function. How many of you have seen this one before? In my day, this was called a step function. Why would we call it a step function? It totally looks like steps, right? Okay. It's kind of interesting, but this is called the greatest integer function, which is really kind of weird. You think the greatest integer, but it's actually whatever that is in the ones position. All right, that's the integer we're looking for, which is kind of weird. It looks like this: y equals, it's got a double bracket. So if you make a bracket and put an extra bar next to it, like that, the greatest integer, so there's a bracket and then you get an extra bar. Okay, it just gets an extra bar. You can do this in your calculator. If you go into the math menu, sorry. You gotta go to y equals first if you want to actually graph it. Go to y equals, and then you go to the math menu, and then arrow. Oh, where? I haven't done this in a long time. Is it number? No, it's int. It's greatest int is what it comes up as. Numeric. Is there int? Under number 5. I don't. Greatest. You think that might be it? Let's give it a try. Let's give it a try. Hey, look at that. Yeah, that's it.
Except mine looks like a wiggly line.
Yeah, mine's wiggly.
Yours is stairs, mine is like...
Why does mine keep going straight? Because we're under...
You're doing,
Oh, I have steps too.
Oh, you're supposed to go on the y equals, you're saying.
yeah.
I didn't do that.
I don't know why yours is doing that. Let me do this. Let me factory reset. Reset all RAM. Reset. Okay, and then let's see what happens now. So math number 5, zoom 6. There you go. 6.
Yes, you're just doing that.
Genius. Okay. So this is the greatest integer function. And so what's interesting is if you like trace and say, hey, what's the greatest integer of some like 0.589? All right. What's the greatest integer of 0.589? Well, it's 0. What's the greatest integer of 1.269? What's the greatest integer of 1.269? Just 1. Okay. What's the greatest integer of 6.124? 6. Okay. That's the greatest integer function. It just gives you that integer. Well, it's great until you do negatives, and it just, I don't know. What's the greatest integer of negative 2.356? Negative 3. Blows my mind. Yeah, it's the opposite because we're in negative land. So, it's down below because it's actually lower than the decimal itself. It's kind of weird. So let's try another one. What's the greatest integer of negative 4.621? Negative 5. All right, because we're in negative land, we're going to the integer lower than the actual value. All right, one more. Here we go. What's the greatest integer of negative 6.87 or 89? Negative 7. Okay, so it's kind of a weird kind of graph, but this is the greatest integer function. Is it a function? Does it pass the vertical line test? Yes, it does. Now, we do want to be a little careful, and this is a good thing to talk about. This is a solid dot. The value of the function at 1, f of 1 equals 1. This dot is an open dot. It's not included. Okay? So there really is just one actual point there. Okay? And so it does pass the vertical line test. What is the domain? Negative to positive infinity. It is. We get every single x value in there. It just looks weird. Is it discontinuous? Yes. Discontinuities. It has every integer. There's a discontinuity. Every integer. What are integers? Positive and negative whole numbers. So there's a discontinuity at 1, at 2, at 3, at 4. -1, -2, -3, -4. There's a discontinuity. A jump discontinuity, if you remember that. This is a jump discontinuity. Okay. All right, well, that's a fun function. That's the greatest integer function. I had, is it odd? I don't think so. That's a good question. It is, yeah, so let's see. If I take, like, this dot, like here is a dot 2, 2. So, Taryn, this point 2, 2 has a stick next to it, yeah? We got a solid dot and a stick. If I rotate that around the origin, it does wind up at -2, -2, but the stick is going the other way. Imagine it spinning around. This open circle would spin around and be at 3, -3, -2. It goes the other way. It doesn't land right on top. So it's neither, yes. It is neither. All right. Oh, good questions. Okay, 2 more. And then we're actually going to do the math that I want to do today. This is the sine function and the cosine function. What's the difference between the two? 0, 0, sine function. Cosine starts up high at 0, 1. Okay. We're going to do a whole course in trig. Okay, and we're going to learn to sing the sine song, which is middle, high, middle, low, middle, middle, high, middle, low, middle. You're going to get so good at graphing sine, cosine, tangent functions. It's awesome. And then the cosine song, it's a really hard song, starts high, middle, low, middle, high, high, middle, low, middle, high. All right, that's the cosine song. High, middle, low, middle, high. Middle, high, middle, low, middle. Okay, all right. Yeah, I do like to sing. Yeah. No, actually, here's the notes. Here's what we're really doing today.
So, this is all for fun?
All for fun? Yes! All right, here's what you're really doing today.
It's like our worksheet? Or is this like
No, this is just notes. All right.
where do we put this in our house?
Well, you're going to use it. It'll help you with the delta math today.
We really have one.
Okay, so here we go. So parent functions, we just talked about all the parent functions, and I need you to focus on the really, really important ones, okay, which we're going to do here. These are 3 or 4 different very important parent functions. Right off the bat, we have this function. What shape is this function? Absolute value v. Very good. So we're going to graph that. We're going to graph the following on the axis provided and label each. So the absolute value v goes through 0, 0, and 1, 1, and 2, 2, and 3, 3, and -1, 1, -2, 2, and -3, 3. So there is our absolute value v parent function. All right, you give yourself a really nice, good graph there. That is our parent function. Now, when we add things or subtract things, we are shifting this graph. What happens to our absolute value graph when we add 5 on the outside of those absolute value bars? It goes up 5. Did you know that, or were you guessing? You know that? So you just did it in algebra 2, yeah. Again, we could graph this if we wanted to, absolute value of x, and we could add 5 on the outside. And we can look at the graph and very easily see that it gets shifted up 5. So that plus 5 shifts up 5 spaces. Outside the function, it changes the y values. Okay? What does the 4 do? It changes the x values. Now, everything with x is wonky. Okay? Everything with x is always messed up. No. It goes to the right. So it goes right 4 units. Now everyone's like, why does it do that? Okay. Why does it do that? Because when you see x minus 4, what do you instantly think it's going to do?
Oh, go
You think it's going to go left because it's negative, right?
It's in an asset value bracket.
Well, so that's not the reason, though, because it does the same thing even if I'm not in, like this. It moves the same way. So what's really going on here is I'm the graph. I'm the absolute value. I'm moving left. Okay? So it's really the perspective.
So,
Okay, so I'm the graph. Okay? So you have to be the graph. Okay? You have to be the graph. Alright? I'm moving left. But you're seeing it moving to the right. Okay? Do you see that? Does that sort of make sense to you? Okay? It's a crazy thing, but if you think about actually being the graph, now that's not the real reason. I'll talk more about the real reason later. But that's what's happening. So this actually moves it right 4. So we're going to, my graph, the graph moves to the left. But visually, it looks like it goes to the right. So we're moving each of these points, right 4, 1, 2, 3, 4, and up 1, 2, 3, 4, 5. And what's nice is once you move the vertex, then it's easy to just plot a couple points adjacent. So there is number 2. Okay. All right, let's look at number 3. How does it shift?
I'm down 7.
Down 7, okay. Down 7 and left 3. Very good. That's the plus 3 is going to visually move it to the left 3. All right, so we're going to go left 3 and down 7. So from my parent function now, always back to my parent graph, we're going to go left 1, 2, 3, and down 1, 2, 3, 4, 5, 6, 7. 6, 7. Okay, and there is number 3. All right, and then we have, on number 4, what does the negative do? Yeah, that is a vertical reflection. I call it a vertical reflection because it's changing the direction vertically, okay? We're going from arms up to arms down. All right, now you have to do, now the question is, when we look at this, this is like a -1 times the absolute value. So that is multiplying the whole function. Should we add 8 first, or should we do the reflection first? Reflection first, why? Because of order of operations. Yeah. We've got to multiply before we add or subtract. Yeah. Okay? So we have to imagine here, what happens to my parent graph? It flips upside down. So I can flip it, sort of imagine it's flipped. I'll just make a little sketch here of it flipped upside down. And then, after it's flipped, now we can shift it how? Left 2 and?
Like left, still your 2.
Yeah, left 2 and? Up 8, okay? So I'm again taking my origin point here, and I'm going to go left 2, 1, 2, and up 1, 2, 3, 4, 5, 6, 7, 8. And it's going downward. All right. And so there is number 4. Okay. I love my worksheets. This is my very own worksheet. Okay. I think it's especially fun when everything is color-coded. Okay. Hey, nice. I love it. Okay, fantastic. So, same thing. What shape is our parent function?
Quadratic.
Quadratic parabola. And the parabola goes through the point 0, 0, oopsie daisy, 0, 0, 1, 1, and if I plug in a 2 and square it, we get 4. So 0, 0, 1, 1, and 2, 4, and -1, 1, and -2 times -2 also gives me the 4. So there is my parent function It's a beautiful parabola. And that is y equals x squared. Look at that parabola. I had a teacher once who was so anal. I remember this very clearly because he was, oh my God, he used to take our tests, right? We'd have tests, the paper tests, always. And he'd sit at the front of the room, actually stand over us. We're all in rows. And he'd be like, Jorge and Amanda, I got 100. And then like this other kid, Khalil, like even Amanda did better than you. Every single test. All right, that's what he did. All right. And like, I got a point wrong because my parabola was a little too sharp on the bottom. That was -1 right there because it was a little too sharp, not quite rounded just right. All right. So anyway, I don't need that level of accuracy. All right, but just telling you how it could be.
Wait, where's the farther point from?
-2,4.
Okay, yeah, it's like that.
Yeah. All right, cool. Let's see. Number 6. What are we doing here?
Moving the graph right.
Right 6. Again, that's a 6 inside, and it's moving it in the x direction, so we're just going to go right 6. 1, 2, 3, 4, 5, 6. And then I'm just going to do my other points there. Why does that look weird? Oh, that's only 3. That's why that looks weird. Okay. There we go. That's what I meant to do. Okay. All right. Got this beautiful parabola. Love it. That's number 6. Okay. Number 7. Number 7. What does number 7 do? What does the x plus 6 do? Left 6 and up 6. Yeah, left 6 and up 6. So left 6, up 6. And then I can't do all the points, but that's okay. We get the idea. So there's number 7. All right. And then number 8. What's happening on number 8? Yeah, we got to flip first, vertical flip, a vertical reflection, and then right 4 and down 5, okay? So we're going to flip it first and then go right 4 and down 5. I meant to do that in red. So flip, we're going to go right 4, 1, 2, 3, 4, and down 1, 2, 3, 4, 5, but my parabola is flipped upside down. All right, so it should look like that. Cool. Let's go ahead and do our parent functions here. What's the shape of the square root of x? Swoop. Square root swoop. All right. You can do the voice too, like swoop. It helps. Swoop. All right. The square root swoop goes through 0, 0, 1, 1, and nice numbers 4, 2, because the square root of 4 equals 2. All right, so there we go. There is our y equals the square root of x graph, 0, 0, 1, 1, and 4, 2. Let's just do number 12. What happens on number 12? Flip it, and then you got to go left 4, and then what? Up 4, yeah? Okay. So this gets flipped upside down, so it's really looking like this now. Gets flipped upside down, and then we got to move it left 1, 2, 3, 4, up 1, 2, 3, 4, down another 1, down another 2. 3, that's 3. Every time, I just can't count. 1, 2, 3, 4. Yeah, there we go. All right. And so it goes like that. There is number 12. Okay. What's the domain of this red graph?
0 minus 6.
What's the domain? How far left and how far right does the graph go?
-4.
-4. Infinite, good. Bracket or parenthesis at -4? Bracket, very good. What's the range? How low and how high does it go?
It goes to 4
Is that the high or the low?
high.
Okay, the high is 4. What's the low?
Infinity?
Negative infinity. Is that what you said? Yeah, when this flips, it flips upside down. It keeps going downward, okay? So this card, even though I drew it, it doesn't quite look like that, but it does continue forever in the negative direction. So negative infinity up to +4 with a bracket on there, okay? Those are good questions. Okay, cool. Let's look at number 13. What shape is number 13? Cubic. Yeah, it's a tall, standing tall, curvy one. It goes through 0, 0, 1, 1, and 2, 8. 2 cubed is 8.
Wait, what was it?
0, 0, 1, 1, and 2, 8. And also the negatives. So we get this very standing tall sort of curve. All right. See how much I've done this? Like, look at that curve. Wowza, huh? Wowza. All right, that's pretty good.
Oh, my pen died.
Oh, that's the worst. Okay.
Skip the heartbeat, bro.
Again, let's go ahead and just do this last one, number 16. What happens first? We gotta flip it, which is a little bit hard. I'm actually gonna go ahead and flip this. Vertically, this point here at 2, 8 turns into what? 2, -8. It flips vertically. It just flips over the x-axis. It's technically a reflection over the x-axis. All right, here I'm at 1, 1. What's its flipped point become?
1, -1.
1, -1. Very good. 0, 0 stays the same. This low point here, excuse me, -1, -1, flips up above the axis. And then -2, -8, -2, 8 flips over. So there's the flipped graph. I'm going to make that one dotted. And then how does it shift from there? Down 4. So this is outside the parentheses, so it's going to go up or down. So this is going to go down 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And this one goes down 1, 2, 3, 4 as well. But I don't need to draw that. Okay. So it looks like that. And that is number 16 right there. Okay. All right, questions on that? Is that pretty good? All right. So you have a Delta mouse. That is kind of cool. Ooh, that was 45 minutes.